Hi everyone, this is the last set of slides for Chapter 9. It will cover percent yield and limiting reagents. So this will use what we've learned in the last two lectures really, and start talking about how to calculate percent yield. And so percent yield will be useful when you actually do reactions, because it will show you how well your reaction went. If you thought you were going to get 30 grams of your product based on some, grams to gram stoichiometry that you did, and you only got 20 grams of your product, this will allow you to calculate how well your reaction went. And then limiting reagents, sometimes you'll see it as limiting reactants. That will tell you, essentially, it will limit how much product you can make. Usually you don't put exactly equal stoichiometric amounts of your two reagents in there. One of them is usually you put in a bunch extra. So that you'll have, actually, I have a slide on it right now. The limiting reagent will be the one that limits or determines the amount of product that can be formed in a reaction. And the reaction will only keep going until that limiting reagent is completely used up. So when that one is, runs out, the reaction will stop. The other one is called an excess reagent. This is the one I was talking about. So one of them will usually limit the amount of product that you can make, right? The amount of stuff you're going to get from your reaction. The other one will be excess. It will be extra. And so that will be the reactant that is not completely used up. So in this kind of picture demonstration, we have carbon, which are the little gray ones, and then O2, which are the blue ones, and they are going to react and make carbon dioxide. So they'll keep reacting until one of them runs out. So in this case, it looks like we ran out of O2, right? If you'll look, there is no leftover, O2 molecules on the right-hand side, but we do have leftover carbon that's just sitting there, right? So the reaction stopped because we ran out of O2. So this would be O2 is limiting, right? Because we ran out of it. And then carbon is excess because there's extra, right? So the oxygen limited how much carbon dioxide we could make, and there was extra carbon floating around. So here's an example. If you were to set the table, you would put one plate, one fork, one knife, and one spoon, just in like a basic table setting, nothing fancy, right? So if you had, 5 plates, 6 forks, 4 spoons, and 7 knives, how many times could you set the table, right? So in thinking about this, we need to figure out how many times could we do like this setup given what we have. And this is a pretty straightforward example, right? Since they're all, for every one table setting, we just need one of each of these things. We only have 4 spoons, right? So we can only set the table 4 times. So that would mean that our limiting item is the spoons, because eventually we'll run out of spoons, right? If we set the table 4 times, now we have no more spoons. We have an extra plate, we have 2 extra forks, we have 3 extra knives, but we ran out of spoons, so we can't set the table, right? We can only have 4 people over for dinner. So this is just kind of walking you through that. So like initially we had all of those, right? And we set the table 4 times, right? And so in the leftover column is telling you how many plates, forks, spoons, and knives you have left over. And since, we ran out of spoons, therefore spoons are a limiting reagent. But obviously, this doesn't mean a lot for chemistry, right? Because we're not going to be setting the table. So let's do one more real-life example, though. If I was to make some peanut butter sandwiches, right? And so I had 8 slices of bread and a very large jar of peanut butter. And, if you want jelly, cool. But right now we're just making bread and peanut butter. And so how many times, how many sandwiches can I make? So thinking about making a sandwich, right? We need 2 slices of bread for every sandwich, and a jar of peanut butter, makes a lot. So our sandwiches are being limited by how many pieces of bread we have. Since we only have 8 pieces of bread, and you need 2 pieces of bread for every sandwich, we can only make 4 sandwiches, right? And we're gonna have a ton of extra peanut butter, because peanut butter, like I said, you have a big jar. So the bread is our limiting item, and peanut butter is in excess. So that's just how it is. So whatever thing we're going to run out of, right, like the bread, our bread is like our limiting reagent. Here we just put limiting item because they're not reacting. The peanut butter is in excess. So here's a picture diagram for you. So if you started with 8 slices of bread and a jar of peanut butter, and you made some peanut butter sandwiches, right? You've run out of bread, but you have extra peanut butter left over. So your bread limited how much, how many sandwiches you could make. All right, back to chemistry. So if we have 4 moles of hydrogen and we mixed it with 2 moles of chlorine, how many moles of HCl can form? So this is a reaction, right? The first thing that we have a reaction going on here, right? Because we have, we have hydrogen, we have chlorine, and HCl, we need to write a reaction. So it says H2 is mixed with Cl2. So those will be our reactants. Those will go on the left, and it's asking how many moles of HCl will form. So that is going to be our product. So we can write this here. So H2 plus Cl2, and then I put the 2 out front here to balance our reaction, right? Because we have 2 hydrogens on the left, so we need to have 2 hydrogens on the right. Same thing with the chlorine. We have 2 chlorines on the left, so we need to have 2 chlorines on the right. So the problem says that we're starting with 4 moles of hydrogen and 2 moles of chlorine, and how many moles of hydrochloric acid can we make, right? You'll notice this is different from the problems that we've been doing so far, because normally they only give us one value, and we're trying to find, one other value. Here, they've started us with 2 values, right? We have a number of moles of hydrogen and a number of moles of chlorine. So this is how you'll recognize these limiting reagent problems. They're pretty much always going to give you amounts of both of the reactants. So they'll give you amounts of hydrogen and amounts of chlorine, and they'll ask how much product can you make. And so we have to figure out which one of these is limiting and which one of these is excess. So you're always going to do 2 separate train tracks. Do not try and cut corners. Don't try and do any shortcuts. You need to figure out the moles of product. And so here, right, we're finding moles of HCl from each reactant. They are 2 separate calculations. So you're going to do 2 separate train tracks. One of them will put hydrogen, right? And we'll figure out how many moles of hydrochloric acid. The other one will start with moles of chlorine and figure out how many moles of hydrochloric acid. And the limiting reagent is the one that produces the smaller amount of product. Okay, so whichever one produces less, that one is the limiting reagent. It was kind of like back when we had our pieces of bread and our peanut butter, right? The one that produced the least amount of sandwiches, right? The bread produced 4 sandwiches from that jar of peanut butter. I don't know, we can maybe make 20. I don't know, I don't really eat peanut butter, but let's say we can make 20, right? If the bread can only make 4 sandwiches and the peanut butter could make 20 sandwiches, then our bread limited how many sandwiches we could make. We ran out of bread, right? So the same kind of thing here, we're going to figure out how much product we can make from each one of these. So I'll show you how to do this. So here's our reaction again, okay? And then, so the first step, we're going to figure out how much hydrochloric acid we can make from hydrogen. So in the problem, it told us, right, we are starting with 4 moles of H2. We had 4 moles of H2, and we had 2 moles of Cl2, and it's asking how many moles of hydrochloric acid. Okay, so this is kind of like what we were doing in the first lecture of chapter 9, right? Because we're already in moles. What we were doing in the last lecture, right, we had to turn grams, right? We were starting with grams, so we had to turn grams into moles before we could change compounds. Because we are already in moles, we don't have to convert anything into moles because it's already there. So we can just use our mole ratio to convert from moles of hydrogen to moles of HCl. So looking at our mole ratio here, right, there's nothing here in the front. So that means for every 1 mole of H2, and then it's going to make 2 moles of HCl. So we can continue our train track, right? Looking at that, for every 4, right, if we have moles of H2, that has to cancel down and to the right with moles of H2. So we put 1 mole of H2 on the bottom, 2 moles of HCl on the top, and we double check moles of moles of H2 cancels moles of H2, and we have moles of HCl on the top, which is what we were trying to find. In this particular problem, it only asked us to solve for moles of product, not grams. So we can go ahead and stop there. So then we can calculate how much product will actually form. 4 times 2 gets us 8. So that is how many moles of hydrogen we could make from the amount of how many moles of hydrochloric acid, HCl, we could make from this amount of hydrogen. We will do the same thing with chlorine, exact same process. So we're going to start with those 2 moles of chlorine. That's what the problem gave us, 2 moles of chlorine. And then we need to use our mole ratio to convert from moles of chlorine to moles of HCl. So there's nothing in the front of chlorine, so that means 1 mole of Cl2, and the 2 in front of HCl is the same, so 2 moles of HCl. So we know moles of Cl2 has to cancel moles of Cl2 down and to the right, so that means that 1 mole of Cl2 will go on the bottom, and 2 moles of HCl will go on the top. Double check, moles of Cl2 cancels moles of Cl2, and then we have moles of HCl on the top, which is what we were trying to find. So now we can multiply straight across and get our answer. So those are the amounts of hydrochloric acid we could make from the amounts of hydrogen and chlorine that we started with. So you're always going to get these 2 train tracks. You're going to get 2 answers here. And what you're going to do, you're always going to pick the smaller one. Okay, so if it asked how many moles of HCl would form, we would say this, 4 moles of HCl. That's kind of like when it asked how many sandwiches could we make, right? We could make 4 sandwiches or we could make 20 sandwiches. We always pick the one that's less because now, right, if we tried to make more after this, we don't have any more chlorine. We have run out because we only had enough chlorine to make 4 moles of hydrochloric acid. So we're always going to pick the smaller number. So that means, right, this would be like how much can form, right? This would be the amount, that would be like our answer, how much can form. And then we can go through it. A lot of times it will ask, what is the limiting reagent? So we go back and we look at what was our starting material here. This was chlorine. So chlorine is our limiting reagent or limiting reactant. They're the same, just different terms. So chlorine is our limiting reagent because it is used up first. And chlorine produces the smaller number of HCl. So chlorine would be limiting, which means that hydrogen is in excess. We have extra. Okay, so that's how you would go through if you were trying to convert moles of one thing into moles of another thing. So you try. So this problem says if 4.80 moles of calcium is mixed with 2 moles of nitrogen, which is the limiting reagent? So again, first thing you need to do is write our reaction. I'm going to go ahead and give it to you here because we haven't talked about how to predict the products. But you'll notice that it is balanced. We'd always double check and make sure the reaction is balanced before you start doing this whole process. Otherwise, if the reaction's not balanced, you're going to get the wrong answers. So we are going to do 2 different train tracks. One train track, 4.8 moles of calcium. Another train track with 2 moles of nitrogen. And for both, you're going to figure out how much calcium nitride you can make, right? How many moles of this. So if you're feeling confident, go ahead and pause, try this out, figure out which one of those is limiting. All right, I'm going to go through the solution. So the first train track, we'll put calcium, right? So that 4.80 moles of calcium. So we'll put that, and then we look, right? And we're already in moles, so we can just use our mole ratio to figure out how many moles of calcium nitride. Again, since we're not in grams, we don't need to convert and do anything. So we can just go directly to the mole ratio. So we're going to look at the numbers in the front. So 3 moles of calcium equals, right? And there's nothing here. So 1 mole of calcium nitride. So we can go through, right? Moles of calcium has to cancel moles of calcium down and to the right. So that means these 3 moles of calcium will go on the bottom and 1 mole of calcium nitride will go on the top. Double check that moles of calcium is canceling moles of calcium. And you finished with moles of calcium nitride just like you were trying to find. So we can go through, multiply the top, divide the bottom, get our answer. So again, that's our first train track. So that would be how many moles of calcium nitride we can make from the calcium. So then we go through and do the same thing for the nitrogen. How many moles of calcium nitride can we make from the nitrogen? So we're going to start our train track with our 2 moles of N2. And again, since we're in moles, we can go directly to our mole ratio step, and we can use our coefficients, right? So we have nothing here, so 1 mole of N2, and nothing here, so that's 1 mole of calcium nitride. So moles of N2 has to cancel moles of N2, so this 1 mole of N2 will go on the bottom, and the calcium nitride will go on the top. So 1 mole of N2, 1 mole of calcium nitride, double check, moles of nitrogen cancels moles of nitrogen. We can multiply the top, divide the bottom, and get our answer. So now looking at this, right, we're trying to figure out which one is the limiting reagent. And remember, the limiting reagent is always going to be the one that produces less product. So, right, this one was less, right? This is the smaller number. 1.6 is less than 2.00. So that means that calcium is our limiting reagent. Okay, and so if calcium is our limiting reagent, then that means that N2 is in excess. And if it asked how much product could be formed, we would say this number, 1.60 moles of calcium nitride. You're always going to pick the one that's smaller. So calcium is completely used up when we have that 1.60 moles of calcium nitride that's formed. Therefore, calcium is our limiting reagent. So go ahead and pause here. Do lecture worksheet problem number 20. All right, moving forward. So it's not always that straightforward, right, where there's only one train track and you're going from moles of one thing to moles of another thing. Most times in chemistry, we are measuring out our starting material in grams, right? That's what our balances measure in. And we would also measure our ending material in grams. So now we're going to figure out, okay, if we start with grams and end with grams, how do we do those calculations? So this will be related to what we were doing in the last set of slides, right? In the grams to grams stoichiometry. So this one is a little bit different. It says calculate the mass of water. Right? Instead of moles, right, now it wants grams produced when 8 grams of hydrogen and 24 grams of oxygen react. So the first thing we need to do is write our chemical equation. So here we are. So we have H2O2 reacting to make 2 H2O. Okay, again, you'll notice that it is balanced. Always, always, always double check and make sure that your equation is balanced. If it's not balanced, you need to go through and balance it before you can do anything. So we are starting with 8 grams of hydrogen and 24 grams of oxygen, and it's wanting to know how much water can we actually make. So we are going to do 2 separate train tracks, which I know sounds like a lot of work. It is. But hopefully, even though it's a lot of work, it's not hard work because you're always going to go through this exact same process. So we're going to make 1 train track from grams of hydrogen to grams of water, and the second train track from grams of oxygen to grams of water, and figure out which one gives us less. So here we are. So for hydrogen, we are starting with 8 grams of hydrogen. And like I've been saying, right, we can only change compounds, right? We can only change over to water through moles, just like we were doing in the last set of slides. So we need to take our grams of hydrogen and turn it into moles of hydrogen using the molar mass. So if we went through, right, and calculated this, it would be 2.02 grams of hydrogen equals 1 mole of hydrogen. Okay, so that would be the molar mass. So we can use that, right? Grams of hydrogen has to cancel grams of hydrogen down to the right. So that means this grams of hydrogen is going to go on the bottom, and 1 mole of hydrogen will go on the top. This mass is just a little more specific. You can use 2.02 as well. And so once we've changed it into moles, right, now we have moles of hydrogen. We need to change it into moles of water. So we're going to do that using the mole ratio, just like we were doing in the last couple steps. So we can see 2 moles of H2 makes 2 moles of water. Okay, so in looking at this, right, moles of H2 has to cancel moles of H2 down and to the right. So that means moles of H2 will go on the bottom, right? 2 moles of H2, the stuff from the left, that will go on the bottom, and 2 moles of water will go on the top. Double check, moles of H2 cancels moles of H2, and we're left with moles of water on the top. In the last set of problems, right, we've been looking for moles of product, but here it wants grams, right? What is the mass of water? So now we're going to take our moles of water and turn it into grams using the molar mass. In this one, so we have 1 mole of water, and its mass is 18.02 grams. Okay. Moles of water has to cancel moles of water down and to the right, so that means that 1 mole of water will go on the bottom, and 18.02 grams of water will go on the top. Double check, moles of water cancels moles of water, and always make sure you're ending with what you were actually looking for, right? The problem says calculate the mass of water, which is in grams, so that's what we've done here. So now we have this whole thing set up. We can multiply all the numbers on the top, divide by all the numbers on the bottom, and get our answer. Now we are going to repeat this exact same process for oxygen. So now we're going to start another set of train tracks. We're going to say, okay, if we had, if we start with the 24 grams of oxygen, how much water can we make from that? So we start with our 24 grams of O2, and we will use the molar mass to convert grams of O2 into moles of O2 using the molar mass. So I'm just going to keep writing things up here. 32.00 grams of O2 is our molar mass, 1 mole of O2. So we can use our molar mass, right? Grams of oxygen has to cancel grams of oxygen, so that stuff on the left will go on the bottom. So there we are. 1 mole of O2 will go on the top. We'll double check. Grams of oxygen cancels grams of oxygen. And now we've changed it into moles of O2. Now we can use the mole ratio to go from moles of O2 to moles of H2O. So there's nothing in front of oxygen, which means that we have, running out of room here. 1 mole of O2 and then 2 moles of H2O. So moles of O2 has to cancel down and to the right. So that means that 1 mole of O2 will go on the bottom, right? The stuff on the left. And 2 moles of H2O will go on the top. Double check, moles of oxygen cancels moles of oxygen. And now we're left with moles of water. So now we'll use our molar mass to convert our moles of H2O into grams of H2O. It's actually going to be the exact same last step that we did in the problem before, because that's always going to be the same. So we can actually just fill that in here, because that molar mass doesn't change. Then now we've got grams of water, so we can multiply all the stuff on the top, divide by all the stuff on the bottom, and we get our answer. So it says calculate the mass of water produced when they react. So now you have 2 answers, and you have to figure out, okay, which one is the right answer. So remember, it's always going to be the smaller value. So we have 71.5 grams of water in the top one, 27.0 grams of water in the bottom one. So that means that this one is how much water will actually be produced, 27.0 grams. So that is telling us then, if this is our answer, right, that's how much water we can make, that means that oxygen was our limiting reagent, because it makes less water, which means that hydrogen is in excess. We have extra. It could make more water if we had enough. Okay. So there you go. Oxygen, like I said, is our limiting reagent. Let's do another. If you are feeling confident, go ahead and try and solve this problem. Okay. It says calculate the mass of carbon dioxide produced when 12 grams of carbon monoxide and 9 grams of O2 react. So I have the balanced equation written for you. If you're like, I got this, go ahead and pause here and try it out, and then resume when you want to see the solution. If you need another example problem, just keep going. All right. So this problem is essentially just the same as the last problem. It says calculate the mass of carbon dioxide produced when 12 grams of carbon monoxide and 9 grams of oxygen react. So again, we have we're starting with 2 reactants, and it's wanting to know how much product we can make. That's how you recognize these limiting reagent problems. So we're going to make 2 different train tracks. One starting with carbon monoxide and figuring out, okay, how much carbon dioxide can I make from that? And the other one starting with oxygen, figuring out how much carbon dioxide can I make from that, and then picking the smaller of those two answers. So here we are. So if we start with 12 grams of carbon monoxide, right, there it is. First thing we need to do is convert grams into moles using the molar mass. So the molar mass of carbon monoxide is 28.01 grams. So we have 28.01 grams of carbon monoxide equal to 1 mole of carbon monoxide. Grams of carbon monoxide has to cancel grams of carbon monoxide down and to the right. So we put our 28.01 grams of carbon monoxide on the bottom, 1 mole of carbon monoxide on the top. Double check, grams of carbon monoxide cancels grams of carbon monoxide, and we're left with 1 mole of carbon monoxide on the top. Then, to convert moles of carbon monoxide into moles of carbon dioxide, we use that mole ratio. All right, so we're going to look at the numbers in the front. We have 2 moles of carbon monoxide, and will give us 2 moles of carbon dioxide. So, moles of carbon monoxide has to cancel moles of carbon monoxide, so that stuff on the left will go on the bottom, and stuff on the right will go on the top. Then we double check moles of carbon monoxide, cancels moles of carbon monoxide, and we have moles of carbon dioxide. Now, we'll change moles of carbon dioxide into grams of carbon dioxide using the molar mass. 1 mole of carbon dioxide is equal to 44.01 grams of carbon dioxide. So 1 mole of carbon dioxide will go on the bottom, 44.01 grams of carbon dioxide will go on the top. Double check moles of carbon dioxide cancels moles of carbon dioxide. Multiply all the numbers on the top, divide by all the numbers on the bottom, and you'll get your answer. You do the exact same process for grams of oxygen, right? So we start with our 9 grams of oxygen. We'll use the molar mass, and I'm going to just kind of go through a little bit faster now. The molar mass of oxygen is 32.00 grams, so that mass will go on the bottom because grams of oxygen has to cancel grams of oxygen, and that is equal to 1 mole, so that will go on the top. Grams of oxygen cancels grams of oxygen. Now we have moles of O2. So now we can use the mole ratio to get from moles of oxygen to moles of carbon dioxide. So there's nothing in front of O2 here, and there's a 2 in front of carbon dioxide here. So for every 1 mole, right, 1 O2, we get 2 moles of carbon dioxide. Moles of O2 has to cancel moles of O2, so 1 mole of O2 will go on the bottom, 2 moles of carbon dioxide will go on the top. Double check, moles of O2 cancels moles of O2. And now we have moles of carbon dioxide. So again, like I said before, this last step is always going to be the same because the molar mass of carbon dioxide doesn't change. So 1 mole of carbon dioxide, 44.01 grams. We double check our units cancel, and then we can multiply the top, divide the bottom. So once you've gotten here, right, it says calculate the mass of carbon dioxide produced. So we always have 2 answers. We're always going to pick the smaller one. So that means 18.9 grams of carbon dioxide is our answer here, which means that carbon monoxide, right, this was our limiting reagent, and this, right, our oxygen was in excess. So there you go. That's how you do those problems. Go ahead and pause now so that you can, so you can work on problems 21 to 23 and then come back once you're done. All right, one last topic for today. The difference between theoretical, actual, and percent yield. So these are used in lab, and they essentially tell you how well your reaction went. So the theoretical yield is the maximum amount of product calculated using the balanced equation. This is what you calculate when determining the limiting reagent. This is what we've been doing so far. So this is on paper. So on paper, if your reaction went absolutely perfect, how much product can you make? What is your, in theory, right? On paper, what amount of your product could you get? The actual yield is the amount of product obtained when the reaction actually takes place. This will be calculated during an experiment. So this would be like in lab. So if you went, you did your reaction, you weighed your stuff at the very, very end, this would be your actual yield. Like what you went and actually put on a balance and you weighed it and then you wrote it down on your lab paper, this is your actual yield that you actually got from doing the actual experiment, right? And so then you can compare them using the percent yield. So the percent yield, we always do the actual on the top. So what you got in lab, that'll go on the top. The theoretical yield, so like on paper, when doing stoichiometry, doing train tracks, what did you get on paper? And you'll divide those up, multiply by 100, and that will get you your percent yield. This is, like I said, these three things are super, super useful. They tell us how well our reaction actually went. So, how do we do it? To calculate the percent yield, the actual yield and the theoretical yield are needed. So, here's like if you were going to bake some cookies. Made a bunch of cookie dough, just like a normal recipe usually makes 5 dozen cookies. So that would be, 60 cookies. The phone rings, you answer it, and while you're chatting on the phone, a sheet of 12 cookies burn and you have to throw them out. It sucks. Now your house smells bad. The rest of the cookies are okay though. So it says, what is the percent yield of edible cookies? So we need to figure out our theoretical yield, our actual yield to get our percent yield. So in theory, right, we prepared enough cookie dough to make 5 dozen cookies. So in theory, we should have ended up with 5 dozen cookies. So 5 times 12, we should have ended up with 60 cookies. But, like things do, right, in lab or, in cooking, something went wrong, right? You talked and you burned the cookies, and so you had to throw 12 of them out. So at the end, you didn't end up with 60 cookies. You ended up with 60 minus 12, so you ended up with 48 cookies at the end. So this was our theoretical. In theory, we should have had 60 cookies. But stuff happens, and so we actually ended up with 48 cookies, which is a bummer. So we had 60 cookies we should have only had 48 cookies to eat. So our percent yield, we always do actual over theoretical. Okay, so actual over theoretical, and then times 100 to get percent. Otherwise, it's a decimal, right? This would be 0.80. So you multiply it by 100 to get a percent. So we had an 80% yield, which really isn't bad, but it's a bummer you missed out on 12 cookies, right? So, back to chemistry though, right? Here's an example percent yield problem. So this one says, without proper ventilation and limited oxygen, the reaction of carbon and oxygen produces carbon monoxide. So there we go. It says, what is the percent yield if 40 grams of carbon monoxide are produced when 30 grams of oxygen are used? Okay, so this gives us 2 different starting materials, right? So this is actually, so you have 2 different values. So I'm trying to tell you how this is different from the problems we've been doing before. If we look back on our limiting reagent problems, they would have given us amounts of the 2 reactants. They would give us amount of carbon, an amount of oxygen, and figure out how much carbon monoxide we're going to make, right? That's how we were doing the problems before. Here, they've given us some amount of product and an amount of a reactant. So this is how we'll recognize that it's different. Rather than having carbon and oxygen, we have oxygen and carbon monoxide. We have a reactant and a product. So this is different. In class, I would do this as a multiple choice problem, but that's okay. We're going to do it together anyway right now. So here's our reaction. So we said, okay, we were starting with, let me see if I can flip back. We were starting with 30 grams of oxygen. And we did the reaction, and we made 40 grams of carbon monoxide, and it wants to know how well the reaction went, essentially. What is the percent yield? So the first thing we need to do is figure out, in theory, if we started with this amount of oxygen, how much carbon monoxide could we actually make, right? This is our actual yield, the way the problem's phrased, Okay, so that means that we did the reaction and we weighed it at the end, we got 40 grams. We're going to use this 30 grams of O2, though, to find out how much should we have made. What is our theoretical yield? Okay, so you have 40 grams, that's your actual. You're going to use the 30 grams of oxygen to figure out your theoretical. So to find the theoretical yield of carbon monoxide, we start with our 30 grams of O2. And we will make our train tracks and do all that, right? So we have to convert grams to moles using the molar mass. So we'll put 32 grams of O2 on the bottom, and that is equal to 1 mole. Double check, grams of O2 cancels grams of O2, and we're left with moles of O2. Then we can use our mole ratio, right? 1 mole of O2 will give us 2 moles of carbon monoxide, looking at our balanced equation. So we have 1 mole of O2 on the bottom and 2 moles of carbon monoxide on the top. Double check, moles of O2 cancel moles of O2. Now we have moles of carbon monoxide. And again, we can use the molar mass of carbon monoxide to turn moles of carbon monoxide into grams of carbon monoxide. And here we are. 1 mole of carbon monoxide gives us 28.01 grams. Double check, moles of carbon monoxide cancel moles of carbon monoxide, and you can multiply the numbers on the top, divide by numbers on the bottom, and you get your answer. This number here, this is our theoretical yield. Okay, so this is like, right, so if you look, we had to do math, right? We had to do a train track. That's how we're getting our theoretical yield. So in theory, we should have had 52.5 grams of carbon monoxide. But as you know, things happen in lab, right? Stuff spills, stuff catches on fire, stuff, right? Weird things happen. So we should have gotten 52.5 grams of carbon monoxide, but when we weighed it at the end, we actually only got 40 grams, which realistically still isn't that bad. I know it sounds bad, but it's really not for a chemical reaction. So then, to calculate our percent yield, we are going to do our actual over our theoretical times 100. So our actual is that 40 grams, right? And the theoretical is 52.5 grams. Multiply by 100 to get our percent yield. Okay, so that would be how you do one of these problems. I have another one for you to try and work through. Try and do this one on your own. When nitrogen and hydrogen are mixed, the reaction produces 16.0 grams of NH3. What is the percent yield for the reaction? So here's your reaction. Here's your possible answers. And if you're feeling confident, like I said, go ahead and try this one. If you're like, man, I still don't get this, then stick around. But if you're feeling good, try it out. All right, so here we are. So our reaction that we had was N2 plus 3H2 gives us 2 NH3. And it said, okay, if we start with 5 grams of hydrogen and, we do our reaction, and then when we weighed it at the end, we got 16 grams of NH3. And it's asking, what's the percent yield? How well did the reaction go, right? So the first thing we need to do is figure out the theoretical yield of ammonia, NH3. And so we'll take those 5 grams of H2 and put it at the beginning of our train track. And then we'll convert that to moles using the molar mass. Double check, grams cancels grams. And then we'll use our mole ratio to convert moles of H2 into moles of NH3. So looking at our balanced equation, 3 moles of H2, right, because that 3 in the front, and then 2 moles of NH3. So moles of H2 has to cancel moles of H2. So 3 moles of H2 will go on the bottom, 2 moles of NH3 will go on the top. Double check, moles of H2 cancel moles of H2. And then we're left with moles of NH3. Now we can use the molar mass of NH3 to convert moles to grams. So we go 1 mole of NH3 is 17.04 grams of NH3. Double check, moles cancels moles, and we're left with grams of NH3, which is what we need to calculate this problem. So we can multiply all the numbers on the top, divide by all the numbers on the bottom, and get our answer. So again, this was our theoretical value, right? We had to do train tracks to get it. So that is our theoretical value. the one that we have up here, this is our actual value. So like some lab experiments were done, we weighed stuff, that's what we actually got. And then to get the percent yield, we do actual over theoretical times 100. So 16 over 28.2 times 100 will give us our yield. So 56.5% yield. So those are the two types of problems we were talking about today. We talked about, how to find the limiting reagent, right? Doing the double train tracks, and then how to get the theoretical yield and percent yield and all of that kind of stuff. So the rest of the lecture worksheets, problem 24 to 26, have to do with this actual and percent yield problems like we were just doing.